All right, so that's how we do our partial pressure using Dalton's law. So let us continue. Now here we have a question, most definitely. So now let's try to solve this question. Now this question, it reads as follows. It says to us, a mass composition, mass, this is very important. They are not saying a mole composition or a volume composition. They say the mass percentage composition of dry air at sea level is approximately as follows, meaning for nitrogen gas, we have 75.5 because it's mass composition, we're going to say grams. Excuse. And then for oxygen gas, we have 23.2 grams. And then for air, we have 1.3 grams. So what is the partial pressure of each component? When the total pressure is 1 atm, when the total pressure is 1 atm, okay, 1 atm. So we want to know the partial pressure of each component, meaning the partial pressure of nitrogen gas, the partial pressure of oxygen gas, the partial pressure of air, meaning this is a combined, this is a mixture. It's more like, you know, I love my container, my beaker. Let's say we have a beaker, I'm just making an example, but obviously this is supposed to be out there in the atmosphere, right? Because we're talking about air, nitrogen and oxygen. But let's say this is our atmosphere. We have nitrogen gas, we have oxygen gas, we have air in it. Remember, air, it is composed of other different types of gases, such as methane, whatever gases. So this mixture of gases, we want to determine the partial pressure of each component. Remember the formula that we use to determine the partial pressure of each component. This is the partial pressure is equals to the mole fraction multiplied by total pressure. We're going to use Dalton's law. We're going to use Dalton's law equation to determine the partial pressure. So that means I want to determine the partial pressure of nitrogen gas, meaning I'm going to use my mole fraction for nitrogen gas multiplied by total pressure. But the thing is, I'm provided with the mass composition instead. So what am I going to do? For nitrogen, I'm going to calculate number of moles. So that means to determine number of moles of nitrogen gas, I'm going the same as mass of nitrogen divided by molar weight of nitrogen. So mass of nitrogen, it is provided to be 75.5 grams divided by molar weight. Nitrogen is 14. 14 times 2 is 28. So we're going to have 28 grams per mole is equals to, on my calculator, I'm going to say 75.5 divided by 28. I get 2.696 moles, and therefore I'm going to do the same. I'm going to determine number of moles of oxygen, number of moles of oxygen gas. It's going to be mass over molar weight. Mass of oxygen is provided to be 23.2 grams divided by molar weight. We know it's 16. Oh, I see chat on the chats. Can you pause? Okay. All right, the matter was attended. So let's continue. So the molar weight for oxygen, it's 16. So we're going to say 16 multiplied by 2 because we have 2 atoms of oxygen, diatomic element. It's going to be 32 grams per mole. And therefore, when you punch this out on our calculator, we're going to say 23.2 divided by 32. How much do we get? We get 0.725 mole. Yeah, that's a correct calculation, right? Yeah. And therefore, let's determine number of moles of air. To determine number of moles of air, we're going to say mass of air divided by molar weight of air. But remember, how do we determine molar weight of? You're supposed to know these things without even calculating, but a quick reminder, if you forgot the molar weight of air, remember, air, it is made up of nitrogen and oxygen. We're going to assume that, okay? So to determine molar weight of air, if you forgot, which is 28, something, something. So you're gonna just say molar weight of average molar weight of air is equals to mole fraction of oxygen gas multiplied by, we use the mole fraction, not the mass fraction, okay? We use the mole fraction of oxygen gas multiplied by molar weight of oxygen gas plus mole fraction of nitrogen gas multiplied by molar weight of nitrogen gas. So mole fraction of air of oxygen, we know that it's 0.21. It's 21%, right? And therefore 16 multiplied by 2, which is molar weight from the periodic table, is most definitely 32, plus mole fraction of nitrogen, we know it's 0.79. You're supposed to know these things. It's 0.79. When you add them, they're supposed to give you 100, right? 21 plus 79 supposed to give you 100, yes. And therefore the molar weight of nitrogen, it's 14 times 2, which is most definitely 28. And therefore when you punch this on our calculator, you're going to say 0.21 multiplied by 32 plus 0.79 multiplied by 28. We get, I don't know if I did the correct thing here. We're going to say 0.21 multiplied by 32 plus 0.79 multiplied by 28. How much do I? Yes, 28. 28,84 grams per mole. So this is the average molar weight of air, okay? If you forgot that is 28,84, perform your calculations quickly, because I know you can't forget mole fraction for oxygen and for nitrogen. You can't forget those two. So that means our mass of air is given to be 1,3 grams divided by molar weight, which is 28,84 grams. And therefore, when we punch this on our calculator, we're going to say 1,3 divided by answer. It's 0,045 moles, right? So remember, we wanted to determine the partial pressures for these. So to determine the partial pressure of oxygen, I'm just going to utilize this space over here because I can see my writing is bad. Don't even have enough space to write. So to determine we're going to use this formula most definitely. So, but before we use this formula, let us determine total number of moles, because to determine mole fraction, we're going to have to remember mole fraction is equals to number of moles of your component divided by total number of moles. Divide by total number of moles. So to determine total number of moles, you're going to say total number of moles is equals to number of moles of oxygen gas plus number of moles of nitrogen gas plus number of moles of air is equals to our oxygen gas number of moles is equals to, where is it? It's 0, comma, I don't see my writing. You see, this is what I hate about myself. Sometimes 23,2 divided by 32, we said it's 0,725, 0,725, 0,725 plus of nitrogen, number of moles of nitrogen, it's 2,696 plus number of moles of air, it's 0,045 moles. And therefore we add them together, we're gonna say 0,725 plus 696 plus 0,045. And then we get our total number of moles to be 3,466 moles. This is the total number of moles of nitrogen, oxygen, and air. So I'll just utilize this formula. I'll just utilize, I'll convert over here. So to determine mole fraction for nitrogen, you're gonna say number of moles of nitrogen, which is 2,696 divided by total number of moles, which is 3,466, and then the total pressure is given to be 1, and therefore you punch this on your calculator. You're gonna say 2,696 divided by 3,466, which is equals to 0,778 ATM. Okay, so for oxygen, you're gonna do the very same thing. What is the number of moles of oxygen? The number of moles of oxygen is 0,725. So you're gonna say 0,725 divided by total number of moles, which is 3,466, multiply by total pressure. Remember, we are using this formula. Multiply by total pressure, which is 1 atm. It's gonna be equals to how much? It's gonna be quick 0,725. It's gonna be 0,209 atm. Okay, and therefore for air, you're gonna do the very same thing. What is the partial pressure of air? Yeah, it's air. You're gonna determine the mole fraction of air and the total pressure. But how do we determine the mole fraction of air? Number of moles of air, which is this 0,045, divide by total number of moles, which is 3,466, multiply by total pressure, which is 1. It's gonna be equals to how much? Now I want to move fast because we have a lot of things to cover. It's 0,045. How much do we get? We get 0,013 ATM. And therefore this is our final answers. Okay, these are our final answers. I hope that was clear. Now, we're going to talk about the kinetic molecular theory, which is sub under the properties of gases. We're still talking about the gases. So I'll just explain this, okay? There's nothing major or difficult about this because basically, I've been talking about this the entire time. It's just that maybe you're not aware of it, that it is called the kinetic molecular theory. So when we talk about the kinetic molecular theory, again, you have to think of gases, okay? You have to think of temperature. You have to think of the speed of the gases, okay? Again, let's say, I love my container. Let's say we have a container like this, and then we have a gaseous molecules in this container. We have gaseous molecules in this container. Now, this is what is happening. We're going to talk about the kinetic molecular theory. What does kinetic mean? It means motion, right? It means movement. It means motion. What does molecular mean? It means molecule. So that means we're going to talk about the motion of the molecules of the gases. So this concept of kinetic molecular theory, it does also apply in solids. It does also apply in the solutions. But because here we are talking about the gases, let us discuss the kinetic molecular theory under the gases, okay? So now this is what is happening. Let's start by talking about the temperature to describe this hypothesis of kinetic molecular theory. So if we have high temperature, let's say this container, it is exposed to high temperature. So that means these gaseous molecules, they will move vigorously in this container. Why? Because these gaseous molecules will take the heat energy, and that heat energy, these gaseous molecules will convert it into kinetic energy. We know that the principle of energy is that energy can be created from one form to the other form, okay? So you have to understand here, we are combining chemistry and physics, hence why physical chemistry. So that means the energy that it is going to be fed into this vessel, which is heat energy, these gaseous molecules, they will take that heat energy and convert it into kinetic energy. Therefore, these gaseous molecules will start moving in different directions chaotically. They will move vigorously in this container. Okay, so the kinetic molecular theory is only based on that most of the times, but there are external factors, but you will see these external factors as time goes by. Okay, so I'm not going to dwell too much on it. Just understand the whole theory behind the temperature thingy. Okay, all right. Now let's go to number 8. Number 8 is called the Graham's law of effusion. Guys, do not confuse this word and this word. They kind of sound similar, but they are most definitely different. So the Graham's law of effusion. So what is effusion? We need to know that. Remember, we are talking about the gases. Okay, think of gases in your mind while we do these concepts. So now, when you talk about the effusion, we say escape of gas molecules. Bona, E, escape. Don't D, escape. E, escape. Effusion is for escape. Diffusion, it talks about the speed, okay? But I'll tell you what is diffusion. Let's start with effusion. Effusion. So effusion, it is the escape of gas molecules through a tiny hole into an evacuated space. Example, tire puncture. I mean, like, you know, tires, right? A tire. So now let's say a car has a tire, and therefore this car, as it travels, it comes across a nail, and this nail will most definitely penetrate into the surface of the tire. And therefore, when you remove the nail, what is going to happen? The gaseous molecule will start to escape out of this tire through this puncture. So the process that is taking place over there, when the gaseous molecules get out of a tire, it is called effusion. Or you can take a balloon. If a balloon has a puncture over here, what is going to happen with these gaseous molecules? Balloon will start to deflate. As the balloon deflate, it's because the gaseous molecules are escaping out of the tiny hole that a balloon has. So the whole process that is taking place there, it is called effusion, escape of gas molecules through a tiny hole into an evacuated space. They can ask you to define this word tomorrow. Okay. Another term is diffusion. I don't know if you are familiar with this word. I think more especially girls, they are familiar with this word. There is something that we call diffuser. I don't know how to spell it like this. Diffuser. Ne? You can buy it at Clicks, not Clicks. You can buy it at Mr. Price Home Sheet Streets. So it's something that looks like this. Ne? It's a bottle. Ne? It's a bottle, and this bottle inside of it, it has a scent, a nice scent like perfume, and therefore there are sticks that are coming out of this bottle like this. So this thing, they call it a diffuser. Sometimes some other diffuser, they come in a form of sachet, ne? like a sherbet sachet. So they come in this kind of form. So what is diffusion? Diffusion is the speed of one substance through a second substance or space. Example, perfume diffused through at room temperature. So this diffuser, this is how it works. I get it, there is a perfume. This perfume, it is in this space. But this perfume, it needs to move out of this space to this space, which is the room. It moves into the room. So that means this perfume over here will diffuse out of this container and occupy the room, and the room will smell nice at the end of the day. So the whole process that is taking place, meaning one molecule, the speed of this perfume over here in a form of gas, will evaporate and therefore occupy the volume, the room. Or a perfume, when you compress a perfume, a deodorant, right? When you compress a deodorant, psh, what is going to happen? The gaseous molecules will attain a speed to move out of this container and fill the room, okay? That's a diffusion, so don't confuse between these two terms. So because here we're talking about the Graham's law of effusion escapement. So what does the law actually states? The law states that Graham's law of effusion escaping, do not forget that. Law states that the rate of effusion of a gas is inversely proportional to the square root of the molar mass. That is, if the rates of effusion of two gaseous substances R1 and R2, and their respective molar masses are M1 and M2, then this is true. Okay, let me try to explain this in a simpler way. Maybe they can also ask you to state the law. So you're going to state the law till here, okay? So you're going to say the rate of effusion of a gas is inversely proportional to the square root of the molar mass. You're explaining this basically, that the rate of effusion of a gas, remember we're talking about the gas, of a gas is inversely proportional to the square root of, this is the square root, to the square root of the molar masses. Now, this is what is happening. This is what they're telling you. Let's say in this container, I have, let's say, nitrogen gas, and then here I have an oxygen gas. So I'm going to apply Graham's law to make this thing make sense to you. So let's say I have it's a container, and then there's my compressor. It's like a spray. Ne? The molar mass of nitrogen compared to the molar mass of oxygen. So what is the molar mass of nitrogen? It's 14 times 2, right? It's 28 grams per mole. What is the molar mass of oxygen? It's 16 times 2 from the periodic table. It's 16 times 2, right? Which is 32 grams per mole. So the molar mass of nitrogen and the molar mass of oxygen are not the same. The molar mass of oxygen is high, and the molar mass of nitrogen, it is low compared to that one of oxygen. So let's talk about the rate of effusion out of this container and out of that container when you spray them in a nitrogen container compared to this one. Because we have low molar mass, remember, rate of effusion, it is inversely proportional to molar mass. When you have low molar mass, that means you're going to have high rate of effusion. So that means in this container, nitrogen, its rate will be higher than the rate of this one. Meaning here, nitrogen will quickly spread out of, will quickly escape out of this container. But oxygen here, it will quickly escape out of this oxygen, not like nitrogen. This will be low, it will have a low rate, and that one will have a high rate escaping. Okay, but remember, you're not compressing, it's all about them. They have to escape by themselves. I hope that was clear. Okay, right. Oh, what happened now? Okay, now let us go to the real case now. Now we're talking reality. Okay, we are done with Graham's law of effusion. Don't forget fusion and effusion and diffusion. So now let's talk about the real gases. Okay, remember, the real gases are not the non-real gases or the perfect gases or the ideal gases. So here we're talking about the real gases. That means we're not talking about ideal anymore. So we say that the real gases do not obey the perfect gas law exactly. Meaning, if I have a real gas, if I have a real gas, and say, for an example, I want to talk about those 4 parameters: volume, pressure, temperature, and all of those 4. To calculate anything that has to do with real gas, I'm not going to use this formula. PV is equals to nRT. I'm not going to use this formula. Because this formula, it's for ideal gases, or we can say it's for the perfect gases, or we can say it's for the non-real gases. So for real gases, I'm not going to use this formula. That means if I want to use this formula to calculate maybe pressure or volume or N or T, if I want to use this formula working with real gases, I'm going to have to correct this formula. But I'll show you how are we going to correct this formula. We're going to introduce the constants such as A and B, but I'll show you how, not now. So we're going to talk about the deviation of real gases and the non-real gases, okay? Firstly, before we can correct this formula. So that's what I'm saying to you. Real gases do not obey perfect gas law exactly, meaning real gases do not obey this thing. We have to correct it first. So now let's talk about the first deviation, okay? How is real gas deviating to ideal gas or whatsoever? I'll explain after this what is happening. So we're going to focus on here, and then after we're going to move here, and then there is the third final one. So let's say we have a container like this, right? And then we are most definitely having the gaseous molecules. These are the gaseous molecules. So now, what do you see in this container? What do you see? What's happening with one of the variables, V, P, N, R, or T? What do you see in this container? Okay, I see that my gaseous molecules are compressed. That means my gaseous molecules, they have high pressure, right? My gaseous molecules, they are under high pressure. And then what's happening with the volume of these gaseous molecules? These gaseous molecules, they only occupying this volume, which is less. I mean, like, check this figure, how big it is. So these gaseous molecules will only occupy this part of a portion of volume. So meaning volume, it is low. Okay. After discussing this, we're going to talk whether this is a real gas or it is a non-real gas. Okay, it's a deviation, you will see. So, okay, there is high pressure, low volume. Now, what's happening with the temperature of these gases? The temperature, let's say we have high pressure and low temperature. The temperature, it is low. Oh, the temperature, it is low. Damn, meaning these molecules are not moving far apart from one another. Because remember, when I was explaining kinetic molecular theory, I said when you heat your gaseous molecules, the speed of the molecules will be high. Therefore, it will cause the molecules to move around the container. But because the temperature here it is low, that means these gaseous molecules are not moving vigorously. They're just, okay, they're chilled, they're cool. Understand? They are not crazy, they're not moving that much. But pressure is high. Now, in this case, what do you see? We see that if we have a low temperature and high pressure, the intermolecular force is phased. That means molecular force is true, intermolecular force is true. We can see that. There is why we say molecular force is true, because repulsive force is more dominant. So that means we have less force drives molecules away. So now intermolecular force is phased. That means these gaseous molecules, they are close to one another, right? They are close to one another. And therefore, we call this condensation point. So when you talk about the condensation point, we say normally it's liquefaction. We say these gaseous molecules will start to liquefy. Because these gaseous molecules are close to one another. I mean, like, for example, take a water vapor, right? When you take a water vapor, like steam of a gas, let's say we have a pot, and then this pot, it is on a stove, and therefore the steam is rising, and therefore let's say we have a plate. This plate over here, it has a low temperature, it's cold. So what is going to happen when this gas gets here, these gaseous molecules, they will combine together. The intermolecular force will exist between them. There will be force of attraction, and therefore as the force of attraction occurs, this water molecule of water vapor will liquefy to form a water in a liquid form, and then you'll start to see droplets out of this surface. It's more or less like something like that. So that's why we say the condensation point. The gaseous molecules will start to come close to one another, and they liquefy to form a liquid. Okay, so that means for a fact that intermolecular force is phased, that means this type of a gas, it is not an ideal gas. It is the real gas. The speed is low. The speed of what? The speed of molecules, because the temperature is low. You see? So that means here we are talking about the real gas. This is how the real gas actually behaves when exposed to these conditions. Okay? All right. So now let's talk about the low pressure. Now let's face this situation over here. Now let's say we have a low pressure. I'm busy. So now let's say now here we have a low pressure. Now, the very same beaker, let's say So that these gaseous molecules, they do not face this high pressure, I'm going to have to lift my lid a little bit up. So under the low pressure, now these molecules are not under high pressure. They can easily move in this, right? Because I have increased the volume now compared to I have increased the volume, right? So that means for a fact that I increase the volume, for a fact that I increased the volume, for a fact that I increase the volume, that means the pressure will be low, inversely proportional. Now, what will happen with these gaseous molecules? Now you have to understand. So we have a low pressure and we have the high temperature. There is this question on tutorial. I think it's question number 1 on multiple choice. So we have, if pressure decreases, volume will increase. Now, these gaseous molecules will experience no, these gaseous molecules will most definitely experience no intermolecular force. For a fact that it seems as if like temperature is high, the molecules are moving far apart from one another. They are crazy. You understand what I'm saying? I mean, like these gaseous molecules will act as if there is no intermolecular force, like there is no attraction between them. There is no repulsion between them. There is nothing. So this means that the gas under these conditions, when we have low pressure and high temperature, gas will behave as an ideal gas. But when we have low temperature and high pressure, a real gas will behave as a real gas. But when we have a low pressure and a high volume, this gas will deviate, this real gas will deviate to an ideal gas. So now this is perfect that, gases, they do not have intermolecular force. So that's how you see it. If I ask you, if I give you a container that has gases, as someone who is not even doing science, you wouldn't even believe there is a force between them. Because I mean, like the gaseous molecules are scattered, they are far apart from one another. So at the back of your mind, that sounds true. That sounds perfect. That's how we see gases. But in reality, the gases have intermolecular forces. But you won't believe that because they are far apart from one another. So that's why we are saying it's a hypothetical gas. So that means under these conditions, we are talking about the perfect gas or an ideal gas when we have low pressure and high volume. Now, here we have moderate pressures. Okay, it's just okay, the pressure, the volume, you see it's like 50-50, this side of the volume, this side of the volume. So here we have the moderate pressure, that means we have the moderate volume. If pressure is high, the volume will be low, but a little bit, you understand? Not high, low, no. It's moderate, it's balanced, kind of. So now what's happening with these gaseous molecules if you have the moderate pressures? We're going to have attractive force, whereby the attractive force is going to be dominated over, attractive force dominate the repulsive force. So that means in this case, these gaseous molecules will attract one another. Okay, attractive force will be stronger than repulsive force. Remember, the repulsive force are only stronger here. Repulsive force dominates, okay? The repulsive force dominates here. The gas is more compressible than a perfect gas because force helps to draw the molecules together. Remember, here we have attractive force between these gaseous molecules. They attract each other. So it's easy for you to compress these gases. Okay, it's highly easy for you to compress these gases. Like for an example, if you want to use an aerosol or a spray. So a spray, that means for these gaseous molecules to be compressed out of this substance. That means the pressure supposed to be moderate in this aerosol so that you can spray, so that it is easier for you to compress them, these gaseous molecules. Why? Because of attraction. So that means this attraction, it helps compressibility of these gases. That's why we say the gas is more compressible than a perfect gas. You can't, it's hard to compress a perfect gas. It's really hard. I mean, like, how can you compress particles that are far apart from one another? This is the real gas, ideal gas. How can you compress this? I mean, like, the particles are far apart from one another, so it's not that easy. The ideal gases are compressible, but not like the gases that has moderate temperature. And here we can say this is the real gas. It's a real gas. Okay, it's a real gas because the intermolecular force exists between these two molecules. You understand? So yeah, and therefore, before we do the last part,